for, like, yeah, in a day. And we'll also review Calculus 1 in recitations tomorrow, okay? So there's a much more thorough sheet you're going to see tomorrow. So there were 3 big ideas in Calculus 1. So limits, remember those vaguely? Derivatives and antiderivatives. Those are 3 big things you're going to have to kind of remember. And the hard thing about Calc 2 is all this stuff keeps coming up again. You can't get away from it. It's like a language class. I cannot leave behind my Russian 101 when I take Russian 102. I have to remember the words I learned there to know the stuff here. It's math is like that too, and that's what makes it so hard. So in general, what a lot of the limits we do deal with this in this class are limits as things go to infinity. So we're going to focus a little bit on those in our review. So informally, what does that mean approximately?
A horizontal asymptote?
It's a horizontal asymptote, yep. So what this could mean also, what I was going to say is that as x gets large, f of x gets close to L. Does that idea make sense? As the x, if you plug in bigger and bigger and bigger x's, the thing that comes out comes closer and closer and closer to that number. And a horizontal asymptote is a great way to visualize it. You have a function, and there's the L, and the function approaches that horizontal asymptote from top. It could approach that limit from the bottom. And in some crazy worlds, it could approach it by doing some kind of like dampening oscillations. Does that make sense? It gets closer to it, the larger the x gets. That's the basic idea. Okay? All right. There are 2 basic tools you have to deal with this. So the first tool is algebra. You may have learned this in like high school algebra 2. And the second tool is something called L'Hopital's rule, or L'Hospital's rule is what it's spelled like sometimes. So can anybody look at this and tell me what the answer is going to be immediately? Negative 1/4. Okay. I'd like to technically review the reason that happens. Okay. On WebAssign, you're allowed to just like give me the answer. Okay. Because if that's that fast, great. But like on the take-home quizzes, I'd like you to show me the why. Does that make sense? So those, you don't have very many questions. I want you to give me your steps and show me your work. So the way that I would think about this is I would divide the numerator and denominator by x squared. And I know it's tedious, but you have to leave that limit symbol there until you've actually done the limit. Since I haven't done it yet, it can't go away. So that becomes 5 over x squared minus 1. Excuse me. 3 over x squared plus 2 over x plus 4. Is everyone okay with what happened there? Yeah. And then what happens as x gets big to 5 divided by a big number squared? That's going to go 0. And 3 over big number squared is also going to go to 0. 2 over big number is going to go to 0. So overall, this thing goes to negative 1/4. So that's the reason why. So on your quiz, if you have a take-home quiz and you're asked to do this, I do want you to show the work, but WebAssign, if you can just see what the answer is, great, that's fine. Okay? So that's kind of the most basic one. Now, can anybody look at this one and tell me where this one's going to go without any work? 1/2. Yep. So we follow the same procedure to show the steps. So we're going to multiply by 1 over x and 1 over x. And the question is what happens to that 1 over x when it goes inside that root sign? So if you have, like, say if you have root 18, you simplify that. That's 9 times 2, oh God, which is 3 root 2, right? Number came out, it got square rooted. To go backwards, it has to get squared, okay? So this becomes root x squared minus 9, and now that 1 over x is back in the root, it's 1 over x squared. And the denominator is 2 minus 6 over x. So that's the limit as x goes to infinity, root 1 minus 9 over x squared over 2 minus 6 over x. And then you can see the things that have x's in the bottom, those are going to go to 0, right? So you end up with root 1, which is 1, yes, over 2. So half. Great. So those are the algebra examples that I have. We'll see them again later, but that's something you just be familiar with. These next two limit problems use something called L'Hopital's rule. So how many of you have heard of L'Hopital's rule? Okay, most of you, good. So if you don't know L'Hopital's rule, it's discussed in detail in section 4.4 of your textbook. That's where it is. So L'Hopital's rule only applies if the limit is of the form 0 over 0 or infinity over infinity. That infinity can be signed, like it can be negative infinity over positive infinity or vice versa. So for this function, what happens to the natural log as x goes to infinity? Goes to infinity. How about root x?
Infinity.
Also goes to infinity. So this is an infinity over infinity thing, and you can use L'Hopital's rule. Usually we say equals, we put a little h, saying we'd be using this little Frenchie's rule. So what this rule lets you do is instead of taking a ratio of the original functions, you take a ratio of the derivatives of those functions and take the limit of that thing instead. They're the same value. So what's the derivative of ln of x? 1 over x, awesome. And how about root x?
Negative 1 over x squared, that root x?
Yep, it'll be 1/2 x to the negative 1/2 or 1 over 2 root x. Does that make sense? Okay. Notice that I did not use the quotient rule, okay? This is the quotient rule that you wished was. Right? Does that make sense?
Yeah.
Okay, now from there, simplify a little bit. So what happens when you have a fraction divided by a fraction? Which one flips? The bottom one does, yep. Limit x goes to infinity. That's 1 over x times 2 root x over 1. I mean, the reason for that is what you do is you multiply by 2 root x over 1 there and 2 root x over 1 there, and the denominator cancels. That's why. And then what happens when you have root x divided by x? They both have exponents, right? When you divide, what happens to exponents? Subtract. So a root is a power of 1/2. What's 1/2 minus 1? Negative 1/2. So this simplifies further to 2 over root x. So the first step was L'Hopital's rule, the rest of it was algebra, right? Now where's that going? 2 over big number? 0 equals 0. Ta-da! Okay. Now, sometimes you can apply L'Hopital's rule repeatedly, like more than once. If you can do algebra to simplify it, you should do that. That's going to be easier. But question, we'll have to do it a few times. If you're a CS guy, CS person, you probably can tell what this is doing because you know about big O, maybe. Okay, so this is going to go to infinity, but we can also explain why with L'Hopital's rule. So is it clear to everybody that this is infinity over infinity? Okay, so if we, Gesundheit, if we L'Hopital it, what is the derivative of e to the u over 10? And then the chain rule, e
1/10.
times 1/10. All over 3u squared, right? Okay. All right. Well, you could technically like simplify this to limit u goes to infinity e to the u over 10 over 30u squared. Do you guys agree with that? How I think about that is if I multiply the top and bottom by 10, it'll cancel out the 1/10, right? But do you still know, you don't know what's happening yet either, do you? Because it's still infinity over infinity, right? Which means you do it again. Yay! And I sense nobody else shares my excitement. I don't know why. So 1/10 e to the u over 10 over 60 u. Crapola. Okay, so I'm tired of this. I don't want to simplify because I'm lazy. So if I L'Hopital it again, limit u goes to infinity, 1 over 100, e to the u over 10 over 60. So now where's that guy going?
Big number over 60,
Big number over 60 and
big number.
still big number, right? That goes to infinity. Whirlwind review of L'Hopital's rule. Okay, so you need to look it up, section 4.4. I may also have a YouTube video of me explaining it to my Calculus 1 class this summer. My YouTube channel name is B.A. Zervis, Alaska. I had a really bad cough for the first 2 weeks, so you might have to hear me hacking through a lecture, but they're available.
Just don't read the comments.
Are the comments bad?
But the YouTube comments were always bad.
Yeah, I don't think I get enough
Is
views
that-
to get
Is
comments.
that also your email?
Yeah,
Okay.
which is also in the syllabus. And on Blackboard under contact instructor, it's you can also Google me and you're gonna find it and other running results. Okay, so given a function, the next big idea is derivatives. So what is the meaning of the derivative? It is the slope of the tangent line, also called a rate of change. It's the reason you've been learning slope for the last 5 years of your life. Seriously, right? It's been forever. So for example, if your function y equaled f of x was population, y prime is the rate of change of population. For example, if that's positive, your population is growing. If it's negative, population is decreasing. Okay, that's kind of the basic idea. So find the derivatives of these functions and state what derivative rules you're using. You're going to have on your review sheet tomorrow recitation, there's tons of stuff about like derivative rules. So like you'll have all the rules reviewed there, but you kind of have to know what they are. So this one is going to use the product rule and also a rule called the chain rule. If you don't know those names, you should be scared. Okay? So the product rule says, so if you take the derivative, you have to say like y prime or dy dx to say what you've done. So the product rule says, first differentiate this function. So what's the derivative of x squared? 2x. You leave the sign of pi x alone. And then plus, now you leave the x squared alone and take the derivative of sine of pi x. So sine's derivative is cosine. And the chain rule part comes and we differentiate that sine of pi x. You multiply by the derivative of pi x, which is pi. And so there you go, that's your derivative. For the interest of time, we're just gonna keep it there. Alrighty. Okay, on this one, there's a rule for quotients called the quotient rule, and I use this goofy little low d high minus high d low over low squared because I'm dyslexic and it helps me. So derivative is, so low means leave lower function alone, so x squared times derivative of e to the 1 over x, which by the way is e to the negative x over x squared, right? Same thing? 1 over x, same thing as x to the negative 1, right? What? Oh shoot, I boo-booed. I'm so sorry. That should say not e to the negative x. It should say e to the x to the negative 1. Those are actually different. So sorry. I just boo-booed on the recording. Crap. Okay, so x squared times, what's the derivative of e to the stuff? E to the stuff times the derivative of x to the negative 1, which is going to be negative 1 x to the negative 2. Okay. Okay, so low d high minus high d low is 2x. All over bottom function squared, so what's x squared squared? X to the fourth. Something cancels on the first term. What cancels?
X squared and negative x to the.
Mm-hmm. The x to the negative 2 really is 1 over x squared, right? Which cancels the other x squared. So this is negative e to the 1 over x minus 2x e to the 1 over x to the fourth. Did you have to use the quotient rule? Could you have just ignored that rule existed and used the product rule? You could technically have written this as e to the x to the negative 1 times x to the negative 2 and applied the product rule. That will also work. It's not wrong. It's fine. I just like my rhyme. Okay? Okay, there we go. Ooh, tan inverse, also known as arctan. So rules that must be used include the product rule and the chain rule. So first, differentiate x. What is x's derivative? 1. So 1 tan inverse of 4x. Woohoo! Plus x times, what's the derivative of tan inverse of stuff? In this case, that would be 1 over 1 plus 4x squared, because like 4x goes in for x. And then from the chain rule, multiplies by 4. So that derivative is tan inverse of 4x plus 4x over 1 plus 16x squared. Okay. And tomorrow on recitation on your worksheet, there's like a list of all the derivatives you have to know, and like you'll know what you need to know basically. Like it's in case you've forgotten because you know June, July, and August happened. Okay, natural log. What's the derivative of natural log of things? 1 over the things, yep. So f prime of x will be 1 over secant of 5x plus tangent of 5x. And you have to, because the chain rule multiplied by the derivative of secant 5x plus tan 5x. Oh goodness, okay. Gesundheit. 1 over secant 5x plus tan 5x. Okay, I know it's been ages, but what's the derivative of secant of 5x? So it's derivative of secant x is secant tan. So this is secant of 5x, tan 5x, and one more thing, times 5 because of the chain rule. Plus, how about tangent? Secant squared of 5x and then times 5, right? If you don't know them yet, I suggest flashcards. Okay. Now, this can be simplified actually quite a lot. What is the greatest common factor of the thing up in the numerator? 5 and... I think they have a secant in common, right? Yeah. So that's 5 secant of 5x times tangent of 5x plus secant of 5x over secant 5x plus tan 5x. Can anything cancel? Those can't cancel. You only can cancel if they're factors and they sort of divide to 1. The tan 5x plus secant 5x can cancel with the tan 5x plus in the bottom. So that just becomes 5 secant of 5x. And a warning, WebAssign is kind of picky about some things. If you don't put these parentheses there, it will tell you that you're wrong. I wouldn't do that on a test or a quiz, but because it's a computer system, you just have to follow their syntax. So if you think things should all be in a function, just put them in parentheses. It's just a good rule of thumb, okay? Alrighty.
Does it count you wrong if you put too many parentheses?
As long as they match up, I don't think so.
Okay.
But I'm not positive, okay? I think you could probably inundate it with too many where you confuse the system, but I'm not sure. I wouldn't, don't try. Yeah.
Is the link on Blackboard to WebAssign?
Mm-hmm.
Okay.
Yep. There's directions in the syllabus as to how to get there. Yep. Okay. Now, another big thing we did other than just taking derivatives was the purpose, like a derivative's purpose in life was to tell you what functions do, right? One big application was you use derivatives to figure out where functions are increasing and decreasing, right? If your derivative is positive, then what happens to your function f?
Increase.
F is increasing. Remember, positive derivative means positive slopes means going up, right? What if your derivative is negative?
Decreases.
Mm-hmm. And the way you figured these out is you, sort of one is probably you took f prime, two was you looked for where does the derivative equal 0, right? And the third thing you did probably is made a sign chart of some sort that kept track of where the derivative was positive and negative, right? It's kind of the procedure. Okay, that's going to happen again in this class, specifically chapter 9, section 3, no, 11, section 11.3, 11.5. But again, so let's use that to figure out where this function is increasing and decreasing. So you must use the product rule and the chain rule in taking a derivative, yep. So this will be 1 e to the negative x plus x times, what's the derivative of e to the negative x?
Is it negative e to the negative x?
It's negative e to the negative x. It's e to the negative x times the derivative of negative x, which is negative 1. Okay. So set that equal to 0. I would suggest factoring out the greatest common factor, which is
E to the negative x.
Times 1 minus x. And then you say, okay, where does 0 equal e to the negative x, and where does 0 equal 1 minus x? This first thing never happens. E to stuff is always positive. Next one, x equals 1, right? Okay. So there's your 1. Look at the sign of f prime. So if you take this factored form and plug in a test number to the left of 1, like 0, for example, is the result positive or negative? E to the 0 is 1, 1 minus 0 is 1, so it's positive. Okay, past 1, something like, 2. E to the negative 2 is some positive number, but 1 minus 2 is negative, yes? So, negative. So therefore, f is increasing on the interval from negative infinity to 1, and f is decreasing on 1 to infinity. 1 is never included because at that point it's changing. So it's kind of it's a no point. It's like a no man's land. In this case, it is indeed a max, yes. It's that pause point where you don't increase or decrease. It's that little crux where you change. So I think technically 0 is like that. Like 0 is neither positive nor negative. It's an in-betweeny. So, okay, so the first thing we're going to go to 11:45, right? So still got time. So the thing we're going to deal with a lot in this class to start is integration techniques. So you learn how to find antiderivatives in Calculus 1 at the very end of your course, probably, right? So given a function f of x that's continuous on the interval from a to b, what is the meaning of the definite integral? What does that tell you? The only technicality of that, it's a great answer, is that this is the signed area under y equals f of x between x equals a and x equals b. And what the whole signed business means is that if your curve goes below the x-axis, that area counts as negative. Do you remember that? Yes? Okay. Alrighty. So far, for you guys, if that function is discontinuous on that interval, you cannot find the area under the curve. We're going to learn how to deal with that in this class. Like if you have an asymptote, you can still talk about the area under the function. It's actually kind of interesting. It's section 7-8, so it's kind of cool. And then what about when you take off the bounds? What does that symbol mean to do? Find the antiderivative. Yeah, so this thing means the correct word is find the general antiderivative of the function f of x. And the whole general business means you're going to have a plus c on the end that accounts for all the different possibilities. That's also called a family of antiderivatives. Meaning like the same sort of base function, different plus c's. They're a family. Okay. So let's start by finding some sort of, and most of the stuff that you know from Calc 1 is like, okay, here's a function. You find the antiderivative by saying, what function do I know who has this derivative? It's just like kind of like a reverse engineering thing, it's a bit of guess and check. And finding antiderivatives is not as easy as finding derivatives. It's much, much harder and occasionally or often actually impossible. You can make up a function right now that myself with my master's degree couldn't do. Like, it'd be really easy for you to do that. So we're going to learn techniques that apply to different things, but there's no hard and fast rules that apply to everything like the product rule or the quotient rule do. So, all right. So don't go making up a product rule for antidifferentiation because there isn't one. You have like a reverse power rule, some sort of general functions you know antiderivatives of, and so if I see a product, the first step you should do probably is to just multiply together, right? You can do that, that's algebra. So integral 0 to 2, 8x cubed, yes, plus 2x minus 12x squared minus 3. If I multiply wrong, please stop me before the mistake perpetuates into like the rest of the problem. I'll take a sip of my coffee and give you a chance to speak. Did I multiply right? Yeah. Okay. All right, so how do you anti-differentiate 8x cubed? So I'm going to say 8x to the 4th over 4, which is also 2x to the 4th, same thing. How about 2x? X squared, yep. 12x squared. 4x cubed. How about the antiderivative of 3? Great. 0, and the little bar says I'm going to plug in 2, and then I'm going to plug in 0. So I have 2 times 2 to the 4th plus 2 squared minus 4 times 2 cubed minus 3 times 2. Plugging in 0 doesn't always give you 0, so just be careful about, like, if it's cosine, plugging in 0 gives you 1, right? In this case, does plugging in 0 give you 0? Yes, so, okay, minus 0. So what's 2 to the 5th? I will be that power on October 16th. 2 squared. You all of a sudden know my age. Okay, minus 2 cubed is 8 times 4 is also?
2.
Minus 6. So I think this is negative 2. So what that means is that between 0 and 2, that curve is more below the x-axis than above it, right? Okay. So that's a pretty basic one. You look at trig functions that have a mild panic attack. Oh my gosh, oh my gosh, oh my gosh. Don't freak out. So keep calm and math on. How about 1 over cosine squared plus cosine squared theta over cosine squared theta? The only way to get good at this is to do lots of practice and observe different tricks and techniques that work. The hint that I would have is that you know an antiderivative for secant squared, right? And 1 over cosine squared makes secant squared, hence that, right? This is sort of unadding the fractions, right? Usually you do this in the opposite way. You add fractions and they have a common denominator, right? This is undoing that. Like you say, a half plus a half is 1 plus 1 over 2, right? It's just going the opposite way. So 1 over cosine squared is secant squared. What's cosine squared over cosine squared? 1. And so what's the antiderivative of secant squared? Whose function do you know who has that as a derivative? Tangent. And what's the antiderivative of 1? In this case, I should say theta since your variable is theta. Does that make sense? But yeah, basic idea. WebAssign will tell you that you're wrong if you use the wrong variable. Okay, so if the question has thetas in it, use thetas in your answer. Morning.
How do you do that?
I think they have buttons you push where you can like push a button that looks like theta.
If you type in.
You also can probably type in theta, like THETA. They make good Scrabble words too. Most of the Greek letters, I assume. Yeah, I bet that's true. Yep, yeah. Either that or they have buttons, but yeah, if you type it in, it'll also work. Okay, so then you plug in pi quarters, so tangent of pi quarters plus pi quarters minus tangent of 0 up 0 plus 0. Habit made that a theta. So what's tangent of pi quarters?
1,
And what's tangent of 0?
0.
0. So 1 plus pi quarters is the answer. You don't have to get a common denominator. You're good. Okay. All right. So the most sophisticated technique you learned in Calculus 1, at least here, my poor AP Calc students back in the day had to learn more techniques because I was mean to them. So the most sophisticated one you have to know for this class is something called the substitution rule. It's covered in section 5.5. If you suck at it, go to section 5.5 and do all of the odd numbered problems for the first 30. Okay, it'll get good at it all of a sudden. So, and this rule basically reverses the chain rule. So the idea is you substitute for what was the inside function, and the letter that they usually use is u. So, and when you make that substitution, the derivative of the thing you substitute has to show up in the integral someplace up to a constant. So here I'm going to substitute x squared plus 4. That's inside the denominator. The derivative of that is 2x dx. And some people do this differently. Like I know like one of our instructors here solves this for dx and like puts that in. It's totally legit to do that as well. I tend to look and see that, oh, I have an x and a dx in my integral. So du is 2x dx, therefore 1/2 du is equal to x dx. And the x dx can be replaced by 1/2 du because those two things are equal to each other. So the x and dx get replaced by 1/2 and du. And then what does the x squared plus 4 get replaced by? U. Another place this comes from is, say, the derivative of u is du dx equals 2x. And you can kind of think that you can separate the du and the dx and move the dx over with the 2x. So it kind of tells you if u changes, how does x change? So, and then you reduce this to something that's really easy to take the antiderivative of. What's the antiderivative of 1 over u? So 1/2 ln absolute value of u plus c, and then just put back in what u was. Technically, in this case, the absolute value bars are redundant because x squared plus 4 is actually always positive, but I won't dock you for being too careful. Does that make sense? Okay. And it just takes some practice to figure out what you should let u equal and just, do some problems if you're confused, but usually it's the inside function. There's some tricky things, but in general, that's the rule. So based on that, what function is inside of some other function? 3 over x. So we're going to try to let u equal 3 over x, or in other words, 3x to the negative 1, right? So then du, what's the derivative of 3x to the negative 1? Negative 3x to the negative 2 dx, or it's negative 3 times 1 over x squared dx, right? Same thing, or negative 3 over x squared.
That works.
It does work. Somebody tried to make a problem that worked, believe it or not. You'd think like I planned this ahead of time or something. All of these problems that you see with substitution are doctored to work. You go to section 5.5, you try them all, they will work, and they have been specially designed to work. And they didn't give you weird ones, they give you ones that work. So the stuff.
10 problems and say 2 of them are impossible.
No, probably not yet. Maybe even ever. So other than you have to know when you've used a different technique, that will actually happen. So the 3 over x gets replaced by u. This is like dx over x squared. I have this bit, so if I take negative 1/3 du, that will equal 1 over x squared dx. So I'm just going to take the 1 over 3rd out in front. There's no more over anything, right? So over 1 du. And then what's the antiderivative of cosine of u? Sine. So just back substitute, you get negative 1/3 sine of 3 over x plus c. Oh, and how could you check all of your answers for stuff that's this simple? They're antiderivatives, right? So you take the derivative of the thing that's in the box, you should get back the thing that's inside the integrand in the beginning. That's what this process is. Okay. Sometimes substituting gets a teensy bit tricky. So here's an example of one that's a teensy bit tricky. And I'm going to start this one but not finish it all the way in the interest of time. So your instinct, what is your instinct that you should substitute for? 2 plus x, because it's the stuff that's inside something else, right? Well, what's the derivative of 2 plus x? It's just 1 dx. And the question is, well, what the heck to do with that x squared? And here's the clever thing. You can take this substitution, and you can actually solve it for x. So if u is equal to 2 plus x, then isn't u minus 2 equal to x? That's just basic algebra, right? So then this becomes the integral of u minus 2 squared root u du. And from there you have to expand and combine powers and stuff. So if you square u minus 2, that's u squared minus 4u plus 4 times root u. That's just algebra. Ooh. What happens to exponents when you multiply root u times u squared? I had lots of people saying that that's just u, and that is wrong. When you multiply common bases exponents, add. What is 2 plus a half? 2 1/2 or 5 halves, okay? Minus 4u to the 3 halves plus u to the, I'm just going to finish the problem, but now I want to. So what's the antiderivative of u to the 5 halves? 5 halves plus 1 is, I think it's 7 halves, isn't it? And then a coefficient of 2/7 minus 4 times u to the 5 halves, coefficient 2/5 plus u to the 3 halves, 2/3. I dropped a 4? Oh, shoot. There's a 4 right there, right? And there's a 4 right there now. Okay, thank you. So it's 2/7, 2 plus x to the 7 halves, minus 8/5, 2 plus x to the 5 halves, plus 8/3, 2 plus x to the 3 halves, plus c. All good? Okay. That is the trickiest u substitution gets, like really. Other than that, if you just pick u to be the inside function, it should work out that the derivative ends up just kind of popping out and being in the function someplace. Mostly they're easy, okay? That's the trickiest it is. All right, now one thing that you have to know how to deal with is how to do substitution when you have a definite integral. And it is really easier to do what I'm going to do in part A. Okay, I'll do part A and I'll start part B to show you how you have to do it correctly, and you can verify for yourself that you get the same answer. So these bounds are technically x bounds, like they're numbers that x is equal to. If you change to u's, you can change to what the u's are equal to. So with this thing, what do you think you'd substitute? ln x. Yep, and the du is the 1 over x dx that is present, right? Now, if x is equal to e, what's u going to equal? U is your substitution. U is ln of e, which is 1, right? If x equals e to the 4th, what's u equal to? 4. ln of e to the 4th, which is 4. So this integral is equal to the integral from 1 to 4, 1 over root u du. What this says is the area under the first curve from e to the 4th is the same as the area under the second curve from 1 to 4. Does that idea make sense? They're different curves, they have different bounds, but their areas are equal. So to find the first area, you can find the second area, which means you can forget the first one ever existed, temporarily at least. So what you can do now is proceed on your way as if this is the only problem you were given and you never saw the first thing to begin with. So what's the antiderivative of that? Well,
2u to the 1/2.
good. Write it as u to the negative 1/2 and then do what they said. The antiderivative of u to the negative 1/2 is u to the positive 1/2 times 2. You add 1, multiply by the reciprocal. 4. So that's 2 root 4 minus 2 root 1, which I think is 2.
Yeah.
Okay. So I'm going to skip part B because I am never going to do it that way. I think it's best if you just figure out this way. There is a way to not change the bounds, and if you do that and you don't change these numbers, it really actually is more work, it's harder. And what you'd have to do at that stage is say equals x equals e, x equals e to the 4th, 1 over root u du, and then you can put back in what the x was in your antiderivative. It will give you the same answer. It takes longer. I'm inherently lazy, and I would like to do things that are the fastest possible. It's so much easier to change the bounds. You just kind of pre-plug in stuff. So, but if you want to see how to do it without changing the bounds, you can look at the notes. As long as you follow the syntax that's there, I'm not going to dock you, but I'm not going to do it that way in class, ever. Okay, one last thing, I'm going to hold you like a minute over, is, okay, last bit. Without doing substitution, can you guess and check the antiderivatives of these things? Because it's going to be really important to be fast at stuff like this. So my first guess is the antiderivative of e to the 4x must somehow involve e to the 4x, right? So if this were the antiderivative, I'd take the derivative of e to the 4x, and I would get back e to the 4x. Is that true?
Yeah.
What's the derivative of e to the 4x? It's 4 e to the 4th. There's an extra 4 sticking out there. It's a little annoying, right? So how would you compensate for that? Put in a 1/4, and then all of a sudden, you've got it. Does that make sense? Okay. You could also have let u equal 4x, and you could have, done the substitution, but it's going to take a lot longer, and it's good for these to be fast, because we're going to need that in a later section. So what's the antiderivative of sine of pi x? So it's going to involve cosine, right? Negative cosine pi x. And then what you're going to need is the coefficient to compensate for the pi. 1 over pi. And then, of course, plus c. Okay. And the last one, how about secant squared of x over 3? Yep, so we're going to have tan of x over 3, and then what goes out in front to compensate? A 3. Yep. You could think about that as the integral of secant squared of 1/3 x. Okay? Thanks for being patient.